Hello, thanks for joining us. Welcome to Additive Manufacturing, Alternatives to Production Parts. My name is Kyle Squillis with Purdue Manufacturing Extension Partnership. I'm joined by Samantha Nelson at Purdue Westgate, and today we're going to talk about everything you can do in manufacturing with 3D printing or additive manufacturing after prototyping, but before you hit end-use part production. This is a little bit about me and my background in manufacturing. I have extensive experience as an operator, programmer, and trainer on 3D printing equipment through a diverse number of deployments in manufacturing. I've been in a job shop environment as well as a production manufacturing environment working in quality, and decided to bring 3D printing or additive manufacturing to as many manufacturers as I can in Indiana and beyond through the Purdue MEP program. So today let's take a look at what we can offer you through Purdue MEP. We want to do these manufacturing site assessments so we can take a look at your floor, either virtually or in person, to see what operations or applications might benefit your production efficiency, your quality, ergonomics, quick changeover time, anything that the additive can apply. For those reasons of growing profitability or saving money. Our workshops and seminars can be both public or private, and we focus on specific topics such as designing parts with additive in mind. We look at technologies compared to one another through a technology demonstration. For example, FDM versus SLA versus material jetting. We also do 3D scanning because 3D scanning or reverse engineering goes hand in hand with 3D printing in so many ways as another digital tool in the manufacturing workflow. Cybersecurity assessments is a growing program for our center. Gene Jones is heading up that division and has a whole other webinar series, a weekly webinar series. I encourage you to check out if cybersecurity is top of mind for your organization. We have some great resources for that. And finally, our collaborative robot site evaluations. This is being done through a new initiative called the iSmart program, where we are holding webinars, virtual events, and eventually in-person demonstrations of various robotics technologies, including collaborative robots, but not limited to that. Could include traditional industrial robots, could be general automation such as sensors, light bars, light curtains, vision systems, and others that manufacturers should be taking advantage of. These events have begun and will continue through the fall of next year, and the goal is to perform these events followed by an assessment if the client wishes to pursue us further, and then acting as a project manager, being a liaison to third-party resources for the equipment, for coming up with developing the business case for the technology, being a matchmaker to those in the automation industry that have a specialty that you're looking for as a manufacturer. So the goal is to deploy automation where it makes sense for our small to medium manufacturers that may not have the resources themselves to devote to that endeavor. So additive manufacturing can be defined as 3D printing at volumes that are beyond the prototype phase, or can include 3D printing for manufacturing activities that obviously support general traditional manufacturing. This is in contrast to 3D printing that it's often thought of as for prototyping, for tinkering, for R&D, not really tied to the manufacturing floor or manufacturing as a business. So that's kind of the distinguishment between the two. Another way to think of it is 3D printing as a step. So printing the part is one step of many, especially when you get into more complex processes, when you talk about removing support, breaking out the parts, blasting, or removing the anchors in metal, for instance, through CNC or wire EDM machining. Finally, of course, to the quality room, for evaluation. These are all steps that must take place as part of the additive manufacturing process. The primary categories for additive manufacturing are stereolithography, material extrusion, material jetting, binder jetting, and powder bed fusion. The acronyms highlighted in gold have the option for metal as well as plastic. You'll notice that material extrusion has a couple different names. Fused filament is FF, or FDM is fused deposition modeling. That is the acronym that Stratasys coined when they invented the technology in the early 90s. Stereolithography was also invented in the late 80s. SLA stands for stereolithography apparatus. Sometimes it's called just SL these days. But those two are really the pioneers, and then the other technologies sort of derived from those original two. The last one there, powder bed fusion, has several options there when you talk about energy source. So whether it's a light-based, a laser-based, or a combination of light and adhesive, powder bed fusion is somewhat of a growing and broad category. Another way to look at these is columns on the left. If they're highlighted in blue, they fall under the technologies at the top. So polymerization is SLA. So plastic and wax for that. Nothing else. Binder jetting or material jetting, they're being lumped together here, can be both ceramic, metal, plastic, wax, and sand, funny enough. So sand is a unique technology. We talk about binder jetting sand for the foundry industry and metal castings. Talk a little bit about that later. Powder bed fusion, ceramic gets added to the fold along with metal and plastic. And then deposition, primarily plastics. There are some metal derivatives that use a deposition technology similar to plastic. And then some of the outliers that don't really fall. Some of the outliers that don't really apply to manufacturing as much would be 3D bioprinting, lamination, printing structures such as concrete printers. Not really as much in the mainstream manufacturing environment at this point. Let's take a look at what HP system looks like in this quick little 90-second video.
HP's multi-jet fusion technology delivers extreme dimensional accuracy and optimal mechanical properties faster. And thanks to HP's unique multi-agent printing process, you have voxel by voxel control over each part. The material is contained within the HP Jet Fusion 3D build unit at all times, meaning the printer can easily switch between a range of different materials. The material is raised from inside the build unit and spread evenly across the build platform where the fusing process occurs. The build platform is then lowered layer by precise mechanisms which help ensure a high degree of dimensional accuracy. At any point during the printing process, you can monitor job status in the command center. The build unit is removed from the printer and taken to the processing station, and the second build unit installed, so you don't have to stop production.
All right, so that was powder bed fusion from HP, which is their multi-jet fusion technology. Again, they also have a metal powder bed fusion system that is in the works, but what's on the market right now is their nylon and TPU. This is a complementary technology, very different in both the footprint of the machine and the material. This is a resin-based, really it's an advanced SLA system. It's based on light, so high-speed light curing a photopolymeric resin that can rival speeds similar to injection molded plastic when you talk about adding multiple machines or a fleet of these machines compared to one injection mold machine. So this technology is from Carbon.
Digital light synthesis combines Carbon's clip technology and programmable liquid resins to enable end-use parts with exceptional surface finish and unmatched mechanical properties. This screw compressor rotor is at the heart of the company Nativis's groundbreaking air conditioning unit. With Carbon, Nativis was able to print the rotor in an advanced material called cyanate ester at a fraction of the cost of the CNC alternative. Here's how Carbon's technology works to print end-use parts. Light from a custom high-performance LED light engine projects a sequence of UV images exposing a cross-section of the part, causing the UV curable resin to partially cure in a precisely controlled way. Oxygen passes through the oxygen-permeable window, creating a thin liquid interface of uncured resin between the window and the printing part, known as the dead zone. Printing with carbon's hardware alone does not allow for end-use properties with real-world application. Once the light has shaped the part, a second programmable curing process achieves the desired mechanical properties by baking the part in a thermal bath or oven. Programmed thermal curing sets the mechanical properties by triggering a secondary chemical reaction, causing the material to strengthen, achieving the desired final properties.
All right. So there's a couple of video examples. Most of you have seen the FDM style printers before. They come in all shapes and sizes. There's a composite version of that with a second nozzle that is really impressive technology from Markforged. Just wanted to show you those two because you maybe haven't seen those in person. Since we're not able to be live with you today, thought those are pretty good examples of some other systems out there. Okay, what do we look for when we're finding applications? So generally, weak applications are those that have standard profiles, standard material thicknesses that can be formed, such as that bracket in the lower center there in sheet metal, as well as that tube that has been bent on a mandrel likely. While those could be printed, should they be? Probably not, because if you have other tools in your shop to create those shapes, and you certainly have access to a material distributor that stocks the tube or the sheet metal in the right thickness, that's probably the way to go. We'll talk about some hybrid manufacturing methods later that you could use to achieve both of those, but anything with standard or machinable or formable profiles, it's not the highest use case for additive manufacturing. Some better ones would be those that have internal passages, such as lattice structures or honeycomb structure, assemblies with higher labor costs or multiple failure points. Think about a welded joint or a riveted piece, such as that piece on the end with the holes shown in this photo. Those can be combined into one single part through additive, because complexity isn't the same issue as it is in additive versus traditional. A lot of the complexity is gone. You still have to design accordingly to additive's rules, but combining parts is a really neat feature that you just can't do through most traditional manufacturing methods, and so certainly not easily. Another way is to produce molds, patterns, tooling for bridge production, or while a tool is being repaired, so that your downtime is minimized and your uptime is increased. And then these production assistance tools, I mentioned that before, but jigs and fixtures are a great place to start when you're taking your journey with 3D printing or additive. And you can see this tool head on the right it's a composite really. It's been printed. The main head has been printed with these internal coolant channels that can only be processed through additive because of their complexity. And then the stock metal inserts have been added to do the cutting. So the high performance, high wear item is still using a production part, but the actual cutting head has been lightweighted to reduce some stress on the machine, as well as added these coolant channels for optimal dispersion of the coolant and removing chips on the stock. All right, production part alternatives. Hybrid manufacturing, jigs and fixtures, pre-production, and supply chain applications. Let's talk about hybrid manufacturing. So this is where you're using 3D printing to produce an asset used in the process other than just the end part directly. These could be tooling such as the mold halves, mold inserts, forming tools, or patterns. It's best deployed when one of those processes is expensive, cumbersome, or has a long lead time. Or maybe you just want to do it yourself and you don't want to rely on a supply chain. Times like now, your supplier may be down, they may be closed temporarily or permanently, and you want more control of the process. this is something that can be deployed. You've got to think creatively. So one firm I'm familiar with, they partner with a foundry, and they print a wax pattern that is then poured with a ceramic slurry over the top of it, and then processed as an investment cast, just like it would in traditional, but it's removed that sometimes complex step of creating the pattern. This is certainly applicable in complex parts or low volume parts where permanent tooling may not be completely justified. So what they do is they print the part, send it to the foundry to do the traditional foundry steps, send it back to the wax printer, who also has machining capabilities, and then they can machine any overgrown areas that were intentional down to a specific tight tolerance. So a lot of castings are machined in certain feature areas, and just like that, you're getting a truly metal part with a lot less time and costs when it comes to the upfront engineering and technician time and creating that pattern for a low volume number of parts. Another example is in thermoforming. Here you've got a plug, a mold, and a heated sheet. The heated sheet is a stock, readily available sheet of plastic. The plug and the mold, they could be traditional milled tooling, but it doesn't have to be. They could be 3D printed. This is what that looks like. So this is an example of a mold that was 3D printed and then finished. A little bit of sanding and painting to give it the crisp detail that the customer desired, and it produced what looks like a common carry-out food tray lid. Everybody's been seeing these lately with COVID, so you would never know that this came off of a 3D printed mold necessarily. But at the same time, if you wanted to iterate this quickly, you wanted to print a couple versions of these to see what worked the best, or if you wanted to just scale up and maybe your quantity's not super high, it's for a pilot run, and you could create several of these without investing tens of thousands of dollars in hard tooling, and that often may be weeks or months out. And printed molds are much quicker to turn around and fairly cost effective. So this is one option in thermoforming that has really gotten a lot of traction in that lower volume custom space. Just going to go back here real quick. So see this little nameplate area in the middle. This is another instance where you could make this a modular piece and 3D print different names for this badge area. Just as they do a traditional tooling, it could be a metal insert, but here you could make a number of these customized according to your different customer demands. So there's more than one application within just this particular mold. The other thing on the performance side, you might notice these little holes that have been designed into the printed part, and that's just to really optimize the vacuum pull of the machine pulling down the softened plastic. So again, less post-processing. You don't have to drill these out manually. These can be designed to not have support and go through the bottom of the mold all the way to where it meets the inside cavity of the part. All right, brake presses. You probably don't think of using printed plastic tooling for brake presses, but it has been done, and with success. So this was taken at FabTech last year when I was there in Chicago, and this particular piece had about 1,000 cycles on it in 14 gauge cold rolled steel or thinner. So it's a pretty good number of parts, 1,000 pieces. The tool started to round and deform a bit beyond that. Depending on your tolerance, though, you could go beyond thousands, or you just print multiple tools. So certainly it could be a bottleneck issue in your own tool room. It could be a lead time waiting on an outside supplier. It could be a cost savings to do these in printed plastic or composite versus the traditional metal tool. A further example of that is this tooling case study where the sheet metal company liked the hundreds of parts they were getting in metal, but they wanted more. So they thought, This printer, it's an FDM style printer, has the ability to be paused. What if we designed first in the CAD file areas for these metal inserts to go to reinforce these high wear areas? Because the part is holding up, but it's wearing out a little bit early right here where that metal mail feature is being bent. So they paused the print, dropped in these metal inserts, and resumed the print and continued until completion so that you would never see the metal parts once they're inside after the die has completed printing. And they were able to get a lot more life out of it. So that ended up being what was 10 days machine to a little over 1 day, printed and processed. And then the cost of $1,400 versus $200 on a punch and die situation for the sheet metal company. So significant findings here. So the composite tooling market is also seeing the benefits of 3D printing. So here you've seen a fully dense metal insert, basically, where it's been inserted into a lighter weight composite wrench. The wear points are focused on a small area in order to keep the tool cost of production down. They didn't print the whole tool in metal. They just made the wear item in metal, and then relied on a lightweight part in the wrench to take over the rest. On the right, usually a best practice here is to design female threading so that metal inserts can be inserted through press fit, through helicoils, through heat staking, a number of different applications. Some have better benefits than others, but particularly fine threads, always better to use a stock fastener such as a metal insert. All right, so jigs and fixtures. Here's just a quick background for those that sometimes might get confused. Jigs are more focused on the tool path, and the fixtures are more focused on holding the workpiece that is having the tool applied to it. Think CNC work holding or product assembly nest when you think about fixtures. Here in this example, the fixture is holding the black part, and the blue printed profiles have been 3D printed to match the profile of the part, and then a metal drill bushing has been inserted into these parts as a drill guide or jig for the handheld drill. You could take this further and make it so that the operator's hand is out of the way and some sort of a clamp is in place. But you get an idea. So we've got 3D printed features, you got stock features for both hybrid assembly as well as achieved through hybrid manufacturing. In the QC lab, 3D printing is really taking hold because these custom profiles that are used to hold and support parts as they are being probed and inspected versus the sometimes lengthy setups that can take place using traditional blocks and pins. A lot of time's being saved and efficiencies are being gained in the QC rooms. You can even add features such as these snap fit removal tools that were added to this nest. Additional features could be multi-durometer surfaces for Class A parts that need to be protected from any scratching or chipping. You can add part numbers into the print itself and use multiple colors so that they are easily identifiable and match up to whatever part you need to work with without having to measure it or inspect it otherwise. So part identification can easily be done through 3D printing and programming the printer with color. So this is a nice little example of both an efficiency savings and an ergonomic one in saving someone's fingers from removing all those snap fits. All right, applications for the plant continued here. I've got highlighted in bold end of arm custom tooling, EOAT as it's sometimes called. That's a huge market that's just continuing to grow using additive. Everybody has different parts they're grabbing and unique profiles that it would be best to not use something standard in a lot of cases. So you can print your own custom profile based on that part in a very low volume setting and then get the best grip and dexterity that the robot can offer by doing so. Lightweighting the end of arm tooling is also a big one. So if it's traditionally a solid metal machine gripper, potentially there's ways to take weight out of that by designing it from the inside out and unlocking what additive really gives you on the software side, and that complexity that just can't be done through traditional manufacturing, and saving a lot of the stress and wear that those robots, with the heavy end of arm gripper, we're used to seeing over so many thousands of cycles. The life of the robot has been extended by lightweighting that, as well as moving at faster speeds potentially. All right, and back to the quality room, gauges and fixtures. We looked at CMM Nest's go-no-go gauges that can be colored red and green, for example, based on the depth or the wear of that surface. So you can see the part on the right has been printed on a RISE machine that uses inkjet printing technology, identification, part numbering, QR codes, lots of applications for that. We look at pre-production activity and internal validation units, external beta test units, sending these to customers, regulatory samples that governing bodies will sometimes request from you in order to get a product available and on the market. And then sales and marketing samples for your own benefit, your own team's benefit, as well as selling your customer on some of the features a new product might have by exploding it, cutting it in half in this case of this turbine assembly. You can even show your maintenance folks how it's going to look, so that the parts are broken out by color. Would you rather look at this, or would you rather look at a complex, busy 2D drawing when you're trying to show somebody what a new turbine assembly is going to look like and how to work on it? So this model could have a lot of benefits for external and internal recipients. Certainly virtual reality and augmented reality is doing a lot of this as well, and I would say would be on par with having the physical model, but until those technologies are adopted, 3D printing these could be another great way to really hit home the value of your product to your customer, as well as shorten the learning curve for maintenance technicians. Here's an industry example that many of you might have heard about, but this was really probably April timeframe that we were full COVID response, needed to react quickly, all hands on deck. What can we use for hospital grade masks for those that are on a ventilator? And these snorkels are being used as a way to convert them to ventilator masks by printing this adapter piece you see here. So this piece could have been 3D printed, certainly, but in order to get full approval and going with it more of a production mentality, what was done was to actually 3D print the mold and the insert while the traditional hard tooling was being developed, so that the downtime was minimal and multiple molds could be printed until the traditional tool was ready to go. So what happened here was they were able to validate the part, and it only cost $300 for the tooling to get the 25 pieces they needed. More could have been produced, and this was done in a matter of 3 days compared to traditional tooling that was a couple $1,000s. Certainly could have been more, depending on who they were using as a tool and die shop. And then the lead time, that could have been a number of weeks, but quite a significant savings both in time and money in this case. Now, the benefits of this are, again, the part looks like a production part. It's in the production material. You would never know it was made off of a 3D printed mold necessarily, so that the part integrity and quality doesn't diminish once you're applying 3D printing to the process. So again, this is another hybrid manufacturing example. Flipping that around on the left, what somebody did was to make these, looks like walkie-talkie handsets using a silicone mold, and they did this by printing the pattern and curing the RTV silicone around that pattern until it was hardened and fully cured. And then with that block of silicone is cut in half or in multiple cavities to be able to pour and remove a part successfully in urethane. So versus printing the mold, this is printing the part and making the mold off of the part. Another example of a printed mold on the right there, the grows green molds. That's a polyjet material that produced a really robust part, again, at the end for a prototype or low volume application. When I say low volume, it doesn't have to be upfront either. It could be spare warranty legacy parts that just need to be inventoried for customers who have parts that break. This could be another application where you're plugging in 3D printing as a valuable tool because it's expensive, it's cumbersome to maintain that fleet of tooling to support a legacy part that's no longer a high seller or in production, but you still have customers with thousands of these out there in the field that you have to support. So 3D printing on-demand molds could be a solution for you. When would you look for those opportunities? When the volume is dramatically reduced at the end of the product's life cycle. Additive allows for production and more on demand because the supply chain and tooling constraints are reduced. So really what you need, going back to my example of the foundry and the wax printer, you need an injection molder and you need someone to 3D print the mold. You don't need to maintain a warehouse full of tooling that probably needs repaired over time because it was run really hard in production. You could transition to printing these tools, qualifying them, and then just repeating that process when the inventory left a certain level that required a fulfillment. Here's one case study where the OEM no longer had the tooling for the part, so they looked to an additive solution which improved the tensile strength over 3.5 times and produced a cost savings of roughly 40% compared to traditional manufacturing. Again, this is a lower volume application where additive came to the rescue because the existing tooling was not in the field of play. This is what a traditional supply chain looks like. You've got your order placed. Is it in stock? Yes or no. More time is being taken if the manufacturing is being performed. Before that part is then stocked in the warehouse, the order is picked, shipped, finally gets to the customer. A lot of steps in there, a lot of touch points. Could this be simplified through a digital fulfillment process? You can offer customization to that customer up front. You can directly build parts based on an order instead of an approximated forecast that is likely going to be incorrect either side of the target. And then finally, you can avoid even shipping. Potentially, you can keep that part as a digital file, and that's the inventory, and have the customer produce it locally on their own printer or through a local printer that is within walking distance or driving distance to be able to be picked up versus relying on a shipping company to ship it to the house or the factory. Shorten that lead time. This would be like last mile manufacturing, similar to what Amazon has been offering with last mile delivery, on demand function that is really just going to disrupt supply chains in the future when it comes to manufacturing supply chains. So can we take advantage of both the traditional and additive manufacturing platforms? Traditional manufacturing in many ways isn't going to be affected by additive when you talk about the infrastructure, the volumes, the efficiencies that are built into it. But what if you're able to build in additive as a transition, like we talked about with those legacy parts that are fulfilling spares and warranty parts for customers throughout the end of the life of a product, while traditional manufacturing is still focusing on those new products that are coming out and in the peak of their production periods. It could also provide flexibility for seasonal markets, depending on if you have really high or really low demand periods, and it's tough to gauge how many parts you're going to need. But perhaps during those low points, you can rely on additive, and to do this in an upfront and proactive manner rather than a reaction. That's really the ultimate goal for companies to employ both methods effectively. Some new ideas would be technologies like this wire arc metal additive technology, which is very similar to a weld technology that would be on the end of a robot arm. and it creates a near net shape. So it's a material safe type of geometry that is then sent to a CNC mill and machined and polished to a very tight tolerance, resembling the part that you see on the right. So you might say, why would I do this if I'm going to mill the part anyway? Well, maybe the material is very hard to get, maybe it's difficult to machine, maybe it's very expensive. Maybe you're repairing a part. There's another option. You can actually set up an existing part and weld using this wire arc technology and then come back and machine it to the proper profile. So this is a really interesting take on additive for metal. Here's a part that was based on a existing exhaust elbow that the casting house was backed up and the rush casting was cost prohibitive, so they were looking at alternative means for producing this. And in a matter of a couple weeks, they were able to build this on a powdered metal system and then precision machine the opening, which you can see top left, that chrome-like finish. That's a machined surface versus the kind of matte, porous-looking part that was printed out of the metal powder. But it successfully ran a series of engine tests and actually cost 50% of the rush casting price, as well as keeping the timeline that was originally intended. So there's a great success story there. And finally, generative design or topology optimization. So this is unlocking the power of software and combining that with the innate feature that complexity is almost free. Complexity is not a hindrance in the way that it is in traditional manufacturing. So the way to unlock that is to come up with these very organic looking optimized shapes that are could be made no other way than through 3D printing. So you can see where the arrow is pointing. The algorithm has generated an optimal profile of geometry based on the inputs given by the designer. Then the designer would come back in and make the necking uniform, put some standard radii in there just to make it a little bit more traditional on the feature side, but still having a very much organic looking aesthetic to it. And this align, like I said, this aligns very well with the benefits of both the software optimization and the technology features of additive, being able to build from the inside out to build very unique structures. Some key takeaways from today. So additive is here to stay, but it is just another manufacturing option. It's not a magic button. In many traditional manufacturing technologies, it's not really a threat. But it is an important tool, and what we do is we can help identify which of these technologies, if any, are a fit for you. I'm a big believer that most manufacturing outfits could benefit from one or more of these technologies, either having it in-house or working with a service provider. Things are changing though. It's an immature technology. It's still evolving, and there's a lot to keep track of. So work with an insider who is aware of the changes and aware of the major players and materials that are on the market, so that you can stay competitive and not have a machine or material that is almost obsolete, similar to buying a smartphone and having it be obsolete in a year or two. Metal is behind plastic technology, but it is coming on strong. There's different derivatives of the powder bed metal. I mentioned the wire arc. There's a lot of investment into producing metal parts affordably and at high quality and tight tolerances. So keep an eye on the metal news in additive. And lastly, we looked at a little bit in that last slide, but seeing parts from the additive perspective is so important. So looking past the complexity and seeing, okay, in a perfect world, how would I design this part if complexity was different? If I didn't have to worry about round holes or undercuts or tool reach, how would I design a part differently? How could I combine parts to be a single part from a multi-part assembly. So that's those kinds of things that really get you to the peak additive utilization level once you've taken some other initial steps. And we can help get you there. Events like today are going to do that. You're going to see more announcements from us on events and webinars. We want to be able to do these assessments for you. We want to be able to benchmark parts and other materials. If you have a printer, if you're looking at other materials or other machines, we can help you do that. Think of us as a neutral third party, but similar to somebody in business development for printers, but very neutral. We have access to the whole array of machines, not just a select few that a distributor might have. So we can really give a broader picture of the full additive market. We can help you choose the right technology. We can put the business case behind it. We can convert an idle printer into a profit center. Not in all cases, but in several. Somebody had one thing in mind for the printer, and it didn't turn out well for whatever reason. But there are other applications out there, more than likely, for that printer. So let me take a look at that for you and see if we can come up with a business plan to make it a profit center and not a paperweight. I can perform an assessment to review your plant or your select part library that you may want to convert to being produced through additive manufacturing. And then, like I said, we can benchmark your existing parts on new machines and materials through Purdue's network of partners. Thanks to Samantha and her group today for helping promote this. You can reach her at SJ Nelson, that's the typo in there, sjnelson@prf.org. They have a great set of trainings down there in Crane, Indiana, and appreciate having them on board today. Thanks so much for your time. Here's my contact info. If you want to jot that down, our workshop schedule is on the web, on our website page. Webinars and events are included under the workshops. Thanks for your attention today. Again, if you have any questions, let me know. See you next time.